All right, by now we have looked at position time graphs and velocity time graphs and what those graphs can show us. For example, the slope on a position time graph is velocity, the slope on a velocity time graph is acceleration, and the area under a velocity time graph is displacement. We've also used those things, the slopes and areas, to find mathematical meaning for questions. So given information or given a graph, we can find displacement, acceleration, speeds, and things like that. But you might be thinking, where are those equations? I thought physics was all about equations. The equations that you might be thinking of actually come from those very things we've been talking about, the slope and the area. So for example, this is a velocity time graph, velocity time graph. And with this, we remember that on a velocity time graph, the slope is equal to acceleration. If we wrote our y equals mx plus b equation for that, so just making an equation out of the line, y is not y, but velocity. M is our slope, which we will use acceleration. X is not x anymore, it's time. And b is our intercept, but notice that our intercept would be the velocity at a time equals 0. And we use the symbol v naught to represent that. It's like a little 0 below the v. Additionally, this velocity that we're talking about is talking about the velocity at any specific time that you choose your time to end. So that final velocity is usually how we denote that velocity. So this is one equation that we get from our graph. But there are other ways to get more equations. So if you remember, we have another method to get some meaningful values, which would be the area. I'm going to shade in the area under the graph and in two different colors for a purposeful reason. So remember that area was equal, under a velocity time graph, is equal to displacement. Move over so you can see. So displacement is going to be equal to the area under the graph. I'm going to label this A1 for area 1 and A2 for area 2. So if displacement is equal to the area, it's equal to A1 plus A2. Now remember, for area 1, it's a rectangle, so displacement is going to be equal to that base times height. And for this particular one, a base of t times a height of v naught. So that's kind of for our yellow highlighted portion. And yes, this is the displacement still. The second area is a triangle. So over here, A2 is going to be equal to 1/2 times the base times the height. So now we'll add in 1/2. Our base is still a value of t, but now our height is not v naught and it's not vf, but it's your final velocity minus your initial velocity. So the height is vf minus v naught. We can simplify this and distribute. So there's quite a few variables. We have two v naughts. Usually we don't want to have a separation of variables, so we will just simplify. So displacement is equal to t times v naught plus 1/2 t. We're going to distribute this in times vf minus 1/2 t times v naught. Notice we have two common terms for v naught, so we will combine those, and 1t v naught minus 1/2 t v naught is equal to 1/2 t v naught, or positive, but we don't have to put the positive in there. Then we have left this plus 1/2 t vf, or v final. We can now see that we have this common term, 1/2 t, and take that out from our equation to simplify how it looks. So displacement equals 1/2 t times v naught plus vf. So this would be another equation we could get. So far we have something where if you have a scenario where you know the velocities, acceleration, and the time, you can solve for one or the other. Or we have displacement, but notice this does not have acceleration in it. We want another equation because this would, again, just simplify our steps that we have to take. So if we look carefully, we can make another equation out of these two. I'm going to just show the simple algebra to get there. I notice that I have this VF minus V naught here. And if I were to simplify this or rearrange the variables, I subtract V naught from both sides, and VF minus V naught is equal to AT. So I now have this common kind of function, and I can substitute AT in for VF minus V naught. So I'm going to rewrite this equation, this whole thing, as displacement equals time times V naught plus 1/2 t times AT. So we just replace the VF minus V naught with AT. We can distribute this in. Oops, we don't have to distribute twice. And we get t V naught plus 1/2 t times AT. So AT squared. That is another equation. Now we have displacement and acceleration related in some way. In general, this term is usually written the other way. It's usually written V naught t plus 1/2 AT squared. So just for form, we will rearrange that and write that down. And you're thinking, but I still want more equations. Notice all of these have time. Time is not something that we always have. No pun intended, but we can find an equation without time by using another graph. This happens to be a velocity squared graph versus position. And if we were to write a y equals mx plus b equation for that, what I mean is I'm just writing an equation to describe the line given, we can find another equation that will help us out. So instead of y, we have v squared. Instead of m, and a detail I need to give you is that the slope of this graph happens to be mathematically twice the acceleration of that graph. You don't need to know why, but that just actually happens to be if you take data and evaluate it. So our slope is no longer m, it's not acceleration because this is a velocity squared versus position graph, but our slope is 2a. Our x variable actually happens to be x this time. And then the intercept, again, we know this is velocity squared, but specifically it's the velocity at that initial position. So v naught squared. For form, we usually do talk about this final velocity instead of just velocity. And x is usually written as delta x to talk about displacement, not just a specific position. So vf squared equals 2a delta x plus v naught squared. That's the last equation. These are called the kinematic equations because they're used to describe that motion. And below we will talk about how you can use that. They're rewritten here for you. And a question is given. Move that up a bit. Okay. The first part notice that the equations are given. I actually do have V naught and VI are kind of interchangeable for initial, so I'm just going to change those all to V naughts for you. Okay, a police officer is sitting on the side of 294 using his radar gun to try and catch speeders. Uh-oh. A red Corvette whizzes by too fast, traveling south on 294. The officer has to accelerate from rest to a speed of 38 meters per second to catch the troublemaker 700 meters ahead of where he started. So the first part says, draw a qualitative motion map in the right margin. Remember, he's traveling south, so that means I want to start north. He's at rest sitting there waiting for people, but then has to accelerate. So as he accelerates, his velocities are getting larger in magnitude. Oh, that should look larger. And he is still traveling south. That one goes off the page until he got to that position. Good thing it said qualitative, so we don't have to worry about how many arrows to draw or anything like that. B asks sketch a qualitative position time graph and a velocity time graph. On our position time graph, we don't know the initial position, so I'm just going to start at the origin. And we notice he starts from rest, so he should have a slope of 0, and then has greater speeds, so therefore steeper slopes, and they should be negative since he is traveling in the negative direction. So we get a curve like this. And you might be thinking to yourself, like, shoot, that's not what I drew. It could have started here and traveled like that as well. We don't know the initial position, so that one might look less awkward. Our velocity time graph, if our initial slope is 0, and then steeper and steeper, and negative and more negative, we should see a velocity time graph that corresponds with something like this. We can also use this to double check our motion map and make sure we're piecing all of this together the same way. If we look at the velocity time graph, we see we're on the bottom half of the velocity time graph, or where the velocities are negative. So that means we're moving in the negative direction, which is accurate. Our velocity vectors are in the negative direction. And the slope on this velocity time graph means acceleration, and we have a negative slope here. So therefore, our acceleration arrows are negative. Everything seems to match up, so let's continue on. It asks what amount of time did it take him to catch the speeder. When we're going through problems like this, I find it easiest to write down everything you know. If you noticed, I highlighted in the problem what we were given, and now I'm going to write it on the side kind of as our givens and then our unknown. So we are looking for the time, so I'm going to write t equals question mark, as we just don't know what time is. We're traveling south, we have to keep that in mind. From rest, so that is our initial velocity, or v naught, is equal to 0 meters per second, to a speed of 38 meters per second. So our final velocity, really the velocity at that time, is 38 meters per second. The troublemaker is 700 meters away when he catches them, so displacement is 700 meters. And this is what I meant by we had to remember that we're going south. We technically have a negative velocity, or negative final velocity, and we should have a negative displacement. So those two values should be negative. With these givens and this unknown, we have to look at our equations and pick which one will work for us. We don't have acceleration, so we cannot use the first one. We don't have acceleration, so we can't use the second one. Notice the fourth one has acceleration, so same story, so we have to choose this one. I'm going to rewrite it. Displacement equals 1/2 t times vf plus v naught. And then a trend that you want to start in this class, especially if you're looking to take higher math classes or go on to AP Physics, is we really encourage you to rearrange your formula to solve for the variable in question before plugging in numbers. And that is for the reason of sometimes we don't have all of the numbers for variables, and variables tend to cancel when we get further and further into the year. So for that being said, just kind of an example of how you do that, we're solving for t, so I want to get t by itself. I would divide by 1/2, or that's kind of like multiply by 2, so 2 times delta x equals t times vf plus v naught. Divide both sides by vf plus v naught, so 2 delta x divided by vf plus v naught equals t. Then we're at a part where we can plug in our numerical values. 2 was given, displacement is negative 700 meters, divided by our final velocity of negative 38 meters per second, plus our initial velocity of 0 meters per second. That's all equal to t. In your calculator, 2 times negative 700 divided by negative 38 gives us a value of 36.8 seconds. That works for that one. We're not done yet. The next question is asking, what was the police officer's acceleration? So the thing that we didn't have, which caused us to use this equation here, it's now asking for. This equation does not have acceleration, so we can't use that one to solve for this. But let's fill out again what we know and kind of repeat what we have as our givens down here. So I'll just, V naught equals 0, Vf equals negative 38 meters per second, displacement equals negative 700 meters, and now we are looking for acceleration. We can look at this and say, okay, we have displacement, and we need to use that. So the one that really helps us out is Vf squared equals 2a delta x plus V naught squared. So I'm going to write that out. And again, solve for a before I plug any of my numbers in. So I subtract over V naught squared and divide by 2 delta x. Then I plug in my numbers, negative 38 meters per second, squared, don't forget to square, minus 0 meters per second, squared, all over 2 times negative 700 meters. If you square that value, it does become positive. You're still subtracting 0, then divide by negative 1400, and you get a value of negative 1.03 meters per second squared. If you went through and did this, you might have forgotten the negative signs, just kind of like above. Above, you would have still gotten the correct time, but for this one, you would have gotten a positive acceleration, and that wouldn't have matched our story. So the negative signs are important to remember. Another thing to think of, you might be like, well, now that we had the time in question C, we could use that first equation. So there is a second way we could have done this one. If we had used time that we solved for, then we would know, or we could plug into that first equation and easily sign. We don't have to deal with squaring stuff. The only problem with that is if your answer here was wrong, then your answer down here would be wrong as well. The way we did it first, we avoided using any of our own work so that if we did have a mistake, it wouldn't have carried through. But let's just do that for an example. So Vf equals At plus V naught. Solve for acceleration. Vf minus V naught over T equals A. Plug in negative 38 meters per second minus 0 meters per second. Divide by 36.8 seconds. And you get an acceleration value that is still equal to negative 1.03 meters per second squared. Hopefully that helped going through how to use these kinematic equations. The back side you have some more practice, and then you can see the answers on the bottom are given for you so you can check your work. Enjoy!